Okay, so now that we're through substitution and elimination, we're through, I think, at least with respect to mechanisms, some of the more challenging stuff in the course. And now we're just going to be learning um, about a couple of more functional groups. And then if we have time, eventually we might get to some NMR. But yeah, as you'll see, now that you know SN1 and SN2 and stuff, we don't necessarily have to write out the mechanism for everything now, because we can just write out SN2 or E2 or something. These are mechanisms apply to a lot of different things, and we'll see that in this chapter. But before we get started, let's just start out with some of the basic stuff. So nomenclature, yeah, I'm not going to get super deep into this, but you take the A and E at the end of something. So for example, this molecule, which many of you are familiar with, we look at the parent chain, it's 2 carbons long, so that would be ETH. And normally if it was an alkane, right, this part would be A and E. But since we see it's an alcohol, we would call this ethanol. So I guess really, what you do is you drop the E at the end, and then you add OL. So I guess you would call this like the infix. And maybe the E you would call the suffix. I don't really know, but you get the idea. The part that changes is this to this. Yeah, if you look at some other things, like for example, actually since we're in a pandemic, something that's really common right now is rubbing alcohol, which is a propane isomer. So this is isopropane, would be the parent chain. So the iso refers to the position of the alcohol group. Oops. And we know that from when we learn nomenclature for alkanes. But yeah, isopropane. So all we do is we take this and we change it from E to OL. And yeah, you know, if you have alkenes and other things in there, there starts to get some complications about how to number the chain. That's really the main thing that you have to worry about. And if you want to learn more about that, you know, you can just go and read about it, either in the textbook or on the IUPAC website. But I think this is fine for us. So when we refer to alcohols, generally we just change the E at the end to OL. So ethane becomes ethanol, isopropane, or what would really just be propane, becomes isopropanol. You know, if we had some other thing here, like this, it'd be 1, 2, 3, 4. That's actually wrong over here. But yeah, so we've got, what is that, butane. So the E would become OL. Okay, so that's good for nomenclature for us. Just so you know what I'm talking about. I doubt we'll have any questions like that on the quiz. Most of that stuff can be named pretty easily with software. Okay, so some other basic things about alcohols. So just like when we talked about carbons, we talk about them as primary, secondary, or tertiary. We can do the same thing with alcohols. One thing you'll notice about alcohols is that, you know, how many bonds can an alcohol really have? Well, it's, you know, it's bonded to one side to a hydrogen. On the other side, that's it. It's just got one bond it can form outside of that. So we don't count them in the same way that we would call a carbon secondary or tertiary. We don't count the number of bonds directly to the oxygen. Instead, we just look to its next door neighbor, the actual carbon. And that defines whether the alcohol is primary, secondary, or tertiary. So here are the carbons, this carbon, and this carbon, and this carbon tell you the identity of the alcohol. So we would call this, for example, we would call this a primary alcohol, and all that means is that the alcohol functional group is on a primary carbon. And this one here would be a secondary alcohol, because the alcohol functional group, again, is on a secondary carbon. And finally, yeah, the last one would be a tertiary alcohol, because that carbon is tertiary. And naturally, you can't have a quaternary alcohol because carbon can only have 4 bonds. And if all 4 of the bonds are bonded to carbon, they naturally can't be bonded to an alcohol. So, for example, this would be a quaternary carbon. If we look at this here, that's quaternary. But if you wanted to add an alcohol group, you can see that you would have to, that makes me really uncomfortable even to just draw it out. You would have to add on a 5th bond here. And that's a big, this is no good, right? So that molecule I'm going to erase because it's painful for me to look at, but you won't have 5 bonds to carbon. So you can't have quaternary alcohol. That's really the only point I'm making here. Okay. The book goes on about this for a while. What are the special properties of alcohols and all this kind of stuff. I think that one example in the book kind of summarizes this whole thing. It's just that hydrogen bonding has a very large effect on boiling points. And we know this from general chemistry, that hydrogen bonds form when you have a very electronegative atom, such as an oxygen, bonded to a hydrogen. So water is the canonical example of a hydrogen bonder. It looks like this. And one of the reasons that water has such a high boiling point is that it has hydrogen bonding in it. So alcohols also can form hydrogen bonds, not quite as well as water, because water can form 2 for every molecule, or it has 2 hydrogen bond donors for every molecule, whereas alcohols only have 1. But if we look at this, if we compare, let me erase this water over here. If we compare these 2 molecules and we just look at their boiling points, what's the boiling point of ethanol? So if you've got 100% ethanol, which is hard to come by outside of a lab, but something like Everclear, the boiling point of Everclear would be really close to 78 degrees C. So like we just said with water, it's going to be less than water, but you can see it's still pretty high. And then if we look at this diethyl ether, which is a constitutional isomer of ethanol, so same molecular weight, what's going to be the boiling point of that? That's going to boil, I have minus 24 degrees Celsius. Oh no, I'm sorry, that's not diethyl ether, that's why. Yeah, this is dimethyl ether, not diethyl ether, dimethyl ether. So dimethyl ether is a gas at room temperature. Its boiling point is minus 24 degrees Celsius, so well below freezing for water. This stuff just boils off. And it's just the difference between these molecules is just that this alcohol can form hydrogen bonds, right? Because it's got a hydrogen bond donor acceptor, whereas now we've removed the hydrogen on this oxygen. And so now the boiling point's much higher. So the intermolecular forces for alcohols are higher. And generally, even small alcohols are liquids. So if we look at ethanol as a good example, or methanol, which is going to be the smallest organic alcohol you can have, this thing is a liquid at room temperature. I don't know what its exact boiling point is, but if you compare it to methane, gas, we know that that is a gas, right? So putting that hydroxyl group on there, that alcohol functional group, has a very large impact on the intermolecular forces and the phases or the temperatures that you'll go through phase transitions and stuff for alcohols. Okay. All of that stuff is mostly just descriptive. We're not going to use that for like synthesis or anything like that, just to give you some feel for what these functional groups are like. Let's see. Yeah, something that may be a little bit more handy, and we know this already, but just a review, is just the acid-base chemistry of alcohols. So alcohols are nice because, or I guess one feature of an alcohol, is that this proton, so now we're just looking at the proton here, is acidic. So if I take this and subject it to some sort of strong base, I can pull that off. And now I have an alkoxide. So when you deprotonate an alcohol, we call it an alkoxide. So alcohol, an alkoxide. So for when we know the name of it, so on the right we have ethanol, you could call this ethoxide. So the OL goes to, let's see. I guess not even the OL, it's the ANOL goes to oxide. So you keep the eth prefix, but you get rid of the rest of it. So yeah, so you can make alkoxides from alcohols by just treating them with base. The easiest way really to do this, so now we'll get into some reactions. So I guess one thing is, what is the strength of the base that you need there? Well, the pK of the alcohol is 15. So you have to use things that have conjugate acids with pKs that are greater than 15. So if you used hydroxide or something like that, you would get some deprotonation. If you wanted to completely deprotonate this, you could use something really strong like LDA or sodium hydride, or what's another one that we know? Sodium amide, something like that. If you were really trying to do this, though, at scale, you don't want to use some sort of fancy base, and you don't want to have the side product that forms from the base in solution. What you can do is you can actually just take, and now we're getting into some reactions here. This is a very light intro to this, but yeah, reactions of alcohols. What we can do is we can take this and just subject it to sodium metal. So put a little 0 on the top just to emphasize that that's not sodium plus, that's sodium metal, which is very, very reactive. It's in group 1. It really wants to lose its electrons, and it will undergo, now it's sodium plus, right? So it's gotten rid of that electron, and it's given that electron to the hydrogen. And what you end up getting off of that is hydrogen gas. So you can take an ethanol or something and actually just kind of stir in sodium metal, and you'll start to see bubbling. And that bubbling that you're getting there is hydrogen gas. Obviously, you have to be really careful if you're doing a reaction like that. You can get a lot of pressure buildup or catch things on fire. If you don't want to deal with sodium metal, because sodium metal is a pain in the ass to deal with, because it's so reactive, you can use sodium hydride, which I mentioned above, and then you get the same thing. But this one follows a little bit more of a normal, or like an easier to write out organic mechanism. So remember, sodium hydride, the sodium in this case is actually positively charged. So what we're really dealing with is H minus. Okay? So I know it's confusing because I just drew sodium metal up there. Sodium metal and sodium plus, I mean, obviously they're the same atom at their core. They have the same number of protons, but they are radically different in terms of how they're going to react. We eat sodium plus. You would not eat sodium metal. Sodium plus here is just a countercation. It could conceivably also be like potassium hydride or something else, right? Okay, so yeah, so what does this mechanism look like? Yeah, this is just a normal acid-base mechanism. Oop, and I see I have a mistake over here. So I would get minus there, and then the sodium, again, is just there to counterbalance the charge, so we have sodium ethoxide. Okay, so just some acid-base chemistry. That stuff is mostly a review. The sodium metal thing is kind of new, but you just put that on flashcards and forget about it. So this would be, if I was trying to put this on a flashcard, I would just call this alcohol to alkoxide. Okay. Yeah, so before we get into like in a lot of these reactions you already kind of know because we did it in the SN2 E2 chapter, we just didn't explicitly call it. reactions of alcohols. But before we get into them, let's just quickly review how we can make them. So we know a lot of different ways to make alcohols. The most obvious one, the first one that we learned, is we can take an alkene to an alcohol. We can make the primary alcohol. We can make a secondary alcohol. If you want to make the primary alcohol, remember we use one set of reagents. If we make the secondary alcohol, we use a different set of reagents. I'm not going to go through all those different things because let's just review. But you should go back in your flashcards and make sure you know them. Obviously, I would say in terms of, especially for the rest of this course and for the second course, knowing how to make alcohols is pretty key. Let's see. Yeah, what other ways do we know how to make alcohols? We could also use, if we wanted to do something from last section, if we just took an alkyl halide, in this case this is primary, and add OH minus, now we can make an alcohol that way. And you could also use some SN1 chemistry if you wanted to. Right, if I took this and subjected it to water, let's say, and just let it sit around long enough, now I can make a tertiary alcohol out of this. So the most obvious, straightforward path in my mind is to use the alkene. I'll just go ahead and write this out. This would be hydroboration, oxidation. And then down here we would use acid catalyzed hydration. And remember, you also know if you want to avoid rearrangement, we have that mercury sulfate reaction that we can also do that I haven't explicitly drawn out. But yeah, so we have the transform from alkenes, and then alkyl halides you can also do some SN1, SN2 type chemistry on it to get them. The SN1, SN2 stuff can be kind of harder to see because it doesn't fit as nicely into a deck of flashcards. Because this reaction, for example, actually let me not use red. This reaction, for example, okay, yeah, it works with hydroxide as a nucleophile, but I could use really any nucleophile here, right? I could use cyanide or something as well. And so it's just, you don't want to have to make a million flashcards. You just kind of have to understand when you have an alkyl halide or something that can be a leaving group, you can take any nucleophile and substitute it for that alkyl halide. And I'll give you some practice. We'll do some practice problems where you do that, but I'm just trying to drive that home here, that even though we haven't explicitly called these, like what I typically tell you to do, we wouldn't say alkyl halide. I mean, you could do this, but it ends up being a lot of memorization because then you have to start wondering, well, and this is just as an example, do I need to put this on a flashcard then? That I go from an alkyl halide to having, some sort of cyano group substitution thing here. And I think you don't want to have to do that, right? Nobody wants to have to sit down and memorize, and you can see how it just gets quickly out of hand. Like, okay, well, I can take this. What if I substitute in a carboxylate? Do I want to have to say that now I know how to go from an alkyl halide? Let's see if I can get this right here. Do I want to have to say that I can go from an alkyl halide to an ether? And have I'm sorry, not an ether, an ester. Do I want to have an individual flashcard for each one of these transformations? I think the answer is no. You want to be able to recognize these patterns of reactivity. I mean, I guess it's a personal decision just based on how you learn, but I would encourage you to kind of really understand SN2 chemistry, look at all the different nucleophiles that can do it, and then just sort of mentally remember like if you can just remember all your nucleophiles, then you can kind of remember all these different types of reactions you can do. That's a lot more powerful. That's a lot more powerful than yeah, sorry, I got a phone call there. That's a lot more powerful than just kind of memorizing things, right? So try to avoid that if you can. Yeah, try to avoid that if you can, and stick to some fundamental understanding of SN1 and SN2 chemistry. Okay, I think that's good for this video. So in our next video, we'll pick up on, so this is just sort of an overview of stuff that you kind of already know, maybe a little bit of new stuff. And in our next video, we're going to pick up and actually learn some real reactions of how to transform alcohols into other things. Okay, it's not a crazy amount of new reactions, but we'll definitely learn a few. We'll learn a couple of mechanisms and stuff as well. So.